Morty, we've got to turn the project in early.
Heyo. Let's get some people in the chat here. Let's get some people, and then we will start. I didn't save that. Oh, no. Oh, no. Let's get some people over here. Video. And let's bring up the Discord. Nice. Close. Okay, there's office hours. Do some confidence intervals. We've already done the full homework. So, with the full homework done, let's do it. Got the live chat. Sign in. Remind me later. Who's all in the chat? Who's all in the chat? Assignment manager. Confidence intervals for the true proportion. Is it called confidence rules for the sample proportion? We should rename that. I think this has got it. This is the homework. We've already done the homework. Confidence intervals for sample proportion quizzes. Okay. Let's check it out. Okay, I think this is interpretation one. So here we go. Okay, is the first one we got right here with Pew Research. So Stat Tool 1, Chapter 13, Confidence Interval, or wait, Chapter 13, Quiz, and Pew Research. Okay. So this one goes to the interpretations of confidence intervals. And when we interpret a confidence interval, we always say I am, or at least I say I am, blank percent confident. We'll have Mubot put the interpretation in the chat right here when we say confidence. Because I say I am blank percent confident that the true blank is contained in the interval blank to blank. Now, they might not always do that on my Pearson. It should be close to that. But you should know this for the test because it could be fill in the blank, it could be multiple choice, or who knows what it'll be. We're still figuring out the new way of doing this question to get the grades back to you even faster. And so when you look at this right here, they take a sample of 1,058 students or people, and then they find with 95% confidence that between 42 to 48% report they're using the internet or they're online several times a day. That'd be like 100% nowadays. So I would say I am 95% confident that the true proportion of people who are online several times a day is between the interval 42 to 48. Someone is 95% confident that if you were to ask all, which is the truth, what percent, like, is it B? It is B, Rylan, you're right. Yeah, I am 95% confident that the true proportion of people who are online all the time is contained in the interval 42 to 48. Not for the sample, because confidence interval is for the truth. 95% confidence intervals, we saw this in the notes today, mean if you were repeatedly make intervals, 95% of 95% confidence intervals contain the truth. So that's what we would expect right there is over repeated interval making, 95% of 95% confidence intervals. They throw the sample size on here. If we collected many random samples of this size, about 95% of the confidence intervals would contain the truth. So that should do it right there. 95% of 95% confidence intervals contain the truth, and that's technically the law of large numbers. Ryland, do you have one you want to do? I can keep doing these right here, and some of these are pretty easy. I'll just keep doing questions, and you can hear the review. But if you're like, Brian, do this one, I'll find it. But we might be able to do all of them and do every single question and explain every single question in a 2019 Pew Research. Why is it all Pew Research? I guess they really like Pew Research. I'm actually No, I was looking Pew Research last night. Interpret the interval in context. Well, there's the interval up there, 29.1 to 30.9. What's the context? The study of, we'll do one next. You got it there. So we would say I am 95% confident that the true proportion of people who think whatever they think this is a good. It's just very doing my Pearson. It might be a real one, Pearson. It might be a real Pew poll or something like that. So one is 95% confident that if you were to talk to all, and this would be all of them, if they were to ask all, there we go. What's the difference between this? There is a no. Yeah, it's not the sample either. This is a very similar question. Explain what 95% confident means. Same thing right here. If we were to collect many random samples, about 95% of the constants would contain the truth. It's literally an identical question. So let's do a new one right here. A study of 902. These are easy ones. I love those. Those are so easy. So easy. Easy questions. Yep, here we go. Okay. And drop another one in. I'll have this one done in a moment. And let's talk the theory behind it. Okay, a study of 902 decisions. To grant parole or not, made by Nebraska Parole Board, another one right there, produced the following computer output. There's an extra space right there, I think. There is. Look at that. Assuming these cases are representative of all the cases that may come, so they're telling you it's kind of a good random sample. That's condition 1 of the interval. Here's your interval. We are 95% confident the true proportion of granted parole is contained in the interval 56 to 62%. So we are 95% confident that the proportion of paroles granted by the board is this. That sounds about right. It's not in the sample. It's for the truth. So, hey, Reptar. Yep, we can do 14 homework too. We get to switch over. This should be it. Yep. And then we got another one here in environmental group. Keep asking some chapter 13s, then we'll hop over. I think this is the one. This is a little more in-depth of a problem, so it will take more than a moment. Those were just interpretation problems. But drop another one if you want, and then we'll do some chapter 14 homework. The environmental group, Oceana. So let's see what they're doing. Now, for this problem right here, what do you think you should do first? If you see a problem like this that has you building an interval, what do you probably need to do first? I'm getting ready to do it. You tell me it, and then at least find me one thing in here. So you see a problem like this. What do you think of first? What do you do first? What will be your first step? You get a problem like this. What do you do? Label that notation. John's here and he knows. So we're going to label the notation. We see that this was the sample size. That's n. This is the proportion they saw in the sample, which is p hat. If p hat is 0.329, q hat equals 1 minus p hat. So q hat, we can just do some quick math in our heads, is 0.671. So that's q hat right there. And I almost have everything I need. What am I missing? You'll see it as I write the equation, which is in the book. It's given on the test. What am I missing right now that I don't currently have? What am I missing? What am I missing? So I have almost all of it, the z-score. The z-score for a 95% constant is 1.96. That remains constant for the z-score. John knows right there, 1.96 found. If you go to the apps, you can do the middle 95% on the curve. Once again, you'll need to go to our apps page right here if you don't know it. It's 1.96 always for z-scores, so you can memorize it. But you can go to the apps page right here, and you can do the between, and there it is right there, 1.96 for the middle 95. It needs to be middle, which is between, and that's a confidence roll for between this and this. So make sure you do that, and we now have the equation. So all we're going to do here is plug the numbers in. We're going to plug in 0. I'll do it up here. 0.329 plus or minus 1.96 square root 0.329. Do I have more room over here now? Sad day. Okay, let's do it down here. 0.329 plus or minus 1.96 square root 0.329 times 0.671 over 1215. Once again, p hat plus or minus z times square root p hat q hat over n. And we just plug in the numbers here. I usually solve the standard error first. That's what this component is on the far right. So the standard error is 0.329 times 0.671 divided by 1215. Make sure to hit square root. A lot of people forget that. And then we're going to times by 1.96, giving us the margin of error, which is about 2.6%. So 0.026. And we can just delete here now and rewrite this as 0.026 because that gives the margin of error. 0.026. There's the margin of error. And then we add and subtract it. So subtracting it's going to get 0.303. It's a band, isn't it? And then we're going to add it, and it's going to be a little over 50. It's going to be 0.355. So 30.3 and 35.5. So 30.3 and 35.5. 35.5. Really, it's a notation question when you look at it. What does this conference journal say about the seafood sold in the country? We are, or I am, 95% confident that the true proportion of correctly labeled seafood or mislabeled seafood is contained in the interval 30 to 35%. There's a 95% chance, or we are 95% confident that the interval contains the true proportion, not the sample. The sample's in the interval because the sample's at the center of the interval. Then the interval has a margin of error around it to contain the truth. Are they valid in their criticism? They claim the sample size was too small. No, as long as they did the sampling properly, it's fine. It would just make the interval tighter. Like, the sample size controls tightness of the interval, not how it was properly collected. So no, as long as the necessary assumptions and conditions are met, they took a random sample, less than 10% of the population, and they meet success failure, they're good to go. There you go. Is there another one in here? That's a really good one to do. Should we do one or two more? Charlie, should we do the full homework? John, Rylan, Charlie, we might be doing the homework now. Charlie says do homework. Do homework. We could do all chapter 14 homework. Do people want to do that? We can literally get all of chapter 14 homework done. We'd start the first question. Done. Let's do it. Let's do it, Reptar. Reptar. It's cool with you? Cool with me too. Let's do it. Okay, and thank you people for being here. I really appreciate it. We're going to jump into chapter 14 homework, which is the same for everybody. So you get those done. You got it done. Okay, chapter. It's so hard to see on my screen. It's like barely off the screen. Confidence intervals from the sample mean. Oh, yeah. Oh, it's only 7 questions. We'll have a little more time. Okay, let's jump into it. Okie dokie. Oh, I love this. I love these questions. Who invented the t-distribution and where did he work? Who invented the t-distribution and where did he work? So who invented the t-distribution and where did he work? Guinness Beer. He worked at Guinness Beer. I sound like Arnold being like, who is your daddy and what does he do? It's an old movie. William Seeley Gossett at Guinness Beer invented the t-distribution, and he published in Biometrica on the probable error of the mean or something like that. So this is question 1 right here. Got it marked. And the T is like the Z, but it's more smashed down. Mr. T comes in and he says, "Appui fou." He smashes it down. It has with it what are called degrees of freedom. The formula for the one sample T degrees of freedom are n-1. We talked about this a lot in class, and it's telling us the degrees of freedom here. So what was the sample size? That's not the question they're asking, but this problem came from a sample size of what? This is a reverse question. This problem came from a sample size of what? What was the sample size in this problem? If degrees of freedom are 20 and it's a one sample T, it was 21 because it's 21 sample size n-1. Now, we know the z-score for a 95% is 1.96, but the T is more pressed down. So probably this is going to be about 2.08. We know a 90% from memorization, you don't need to know this, but I do, is 1.6449. Since it's 1.6449, it's going to be a little more pressed down. It's probably about that. And that's how you solve it. You just think really hard. Don't do that. Let's show how to actually solve it. So to actually solve these, you need to go to the t-applet. So you go to the t-applet here, and every t has with it what? This is how to actually solve it with your knowledge. Every t has with it what's. Every t you enter in, you must enter in the what's. There's infinite t's, and they're all denoted by their different what's. There's infinite t's, and they all have different what's. degrees of freedom. So if you look right here at the degrees of freedom control the shape of the T. There's some birds in the chat right there for you. So with more degrees of freedom, the T actually approaches the normal distribution. We have 28 degrees of freedom. Now for a confidence interval, what do I click? Below, above, between, or outside. What do I click for a confidence interval, where we're going from this to this value for the middle area? What button will I click for a confidence interval? Between. And then I simply enter in 98, and the answer is 2.47. So you simply just plug in the values to the thing. And I'll explain how I figured these out. I know a lot of the classic z-scores, like 1.96, is for this. So think about this. I want you to guess. When there's high degrees of freedom, the z and the t are very similar. Don't look it up, though. If I'm telling you when the degrees of freedom are very high, the z and the t are very similar, what would you guess for the t-score if it's always a little bit bigger, but at higher degrees of freedom, it's very similar to the z? What would you guess right here? Remember, we know the z is 1.96. The t can only be bigger because it's more pushed out. So what do you take as a guess of what the possible t is? And then we'll solve and show it. This is not that high. That would be more towards like 600 degrees of freedom. It gets very, very close. You're very close, John. I don't think it'll accept 1.97, but it will accept 1.99. I don't think 1.97. I don't think it'll accept that. Oh, it did. But I think it's closer to 1.99. I don't. It wouldn't have accepted 1.9. I doubt it would have. John, we say we're giving it 50,000 points in office hours. John just got it by guessing it because he basically guessed the z-score, which I said you can basically do for high degrees of freedom. Computers and software will find it for you. So so the exact answer, John, was how many? It was 81 degrees of freedom, right? I think it was 81. I said 1.99. I thought it was closer to that. And it's about 1.99. Ooh, it's basically 2. It's actually at 60 degrees of freedom. It's very close to 2. I know that one. That's actually where it crosses over at 60. It flips-flops right. Oh, is it 59? Oh, no, it's 60 is where it crosses. 60 is where it crosses from 2 to below 2. So I know that one because I've done this so much. I know that. Well, awesome work right there. W. John in the chat. And that's the first question. Use the applet, but also having some understanding of it. Does everyone get what I'm saying? Like, I want you to understand theoretically that the t is kind of a more accurately calculated z when doing the mean. The t is a more accurately calculated z when doing the mean. And William Gossett created it. We went over it a lot in class and explained the reasoning behind it and talked about the theory a little bit. Okay, the next question right here, question 2. Let's do it. Describe how the shape and center of the t models changes as the degrees of freedom increase. Don't look at their answers. As degrees of freedom increase, what happens to the t? It gets water. Notice the degrees of freedom right here. Going from 1 to 11 to 111 to 1000, it gets water. What is happening to the distribution from low degrees, medium, high, and extremely high? Don't look at their answers even. Just think about it. Low degrees of freedom, medium, high, very high. As the degrees of freedom get higher, the distribution does what? The spread gets smaller, and it actually approaches the normal. It literally turns into the normal. Like T's and Z's have no, once you get to this, you see that T of 1.96 for a 95% confidence interval. If we make this a confidence interval with 95, well, that's the Z score. But if you decrease the degrees of freedom, you can see it's no longer 1.96 for a 95% confidence interval. So the T gets tighter. There's less area in the tails. It approaches the normal as degrees of freedom get higher. So it gets closer to the normal. The center does not change, and it gets more narrow, which means tighter. So there we go. T approaches the normal as degrees of freedom increase. It's a very good thing to know, the theory behind it. And William Gossett made it for smaller samples where the differences are going to be more pronounced due to a lack of outliers collected in the data. We talk about that in class. Just throwing that out there if people remember. Okay, let's do the next question. We're rocking and rolling here. The housing market has slowly recovered from the 2008 crisis. Come on, Mike Pearson, don't do this to us. It's not looking better. Recently, in one large community, realtors randomly sampled 31, which is the sample size, bids for potential buyers to estimate the average loss in home value. That's a fun thing to say. The sample showed the average loss was 8,155 with a standard deviation of 1,664. The first thing I would do is I would identify the notation here. We might not use that, but in a problem like this, and they might when we get to the later parts have us use the notation. Can you tell me any of the notation? And I'll tell you the rest. Any of the notation here. A lot of problems boil down to knowing notation.
Notation.
If you know the notation, you can then figure out what equations to use. Any notation. There's a very easy one. People always go for the easy. Nice job on the Y bar. That is the Y bar. That's the sample mean, and that's the sample standard deviation, and this is the sample size. And we can almost make the interval. You can also, what is one thing we could find out, because we're making a T interval, what is 30? Great job, Rylan. So last thing right here, then I'm going to solve the rest of it or work a little bit more. 30 is what? 30 is what? Degrees of freedom, yep, because it's just n minus 1. Degrees of freedom equals n minus 1 for a one sample t exactly. So we got the degrees of freedom. Got a lot of stuff. Alexis, good to see you here too. 5,000 points. And let's take a look. Successes and failures? That's only for categorical data. So when you see success failures right here, these are wrong because we don't do success failure for quantitative data. So the conditions would be we need to have basically random, which means independent. Check the nearly normal condition using a histogram. We did say that in class today. If you check out one of the things we said, we talked about how to check the nearly normal and go all the way down here. There it is. Looking at the histogram is a one way to check the nearly normal. And see, it says check the independence with that. That's all right. Check the normal population is something that doesn't sound right. Okay, the data are independent from a normal. That's good. Check the independence assumption with random. That's good. Check the normal using a nearly normal histogram. That sounds right. Yeah, so look at a histogram. Make a 90% confidence interval. What is the one bit of notation we are missing to make this interval? We're only missing one thing to make a 90% interval. I'll write the interval for you. We're only missing one thing. What is the one thing we are missing? It said 90% confidence, which is like shading like this. The t-score. So the t-score, you have to look at the degrees of freedom to know which t to use. So the t-score, MeBot's dropping the applet. I've got it open. You go over here, and it's 30 degrees of freedom. So you enter in the 30 degrees of freedom. And then it was 90%. There's the answer. 1.69. Great job. Well, you wouldn't use random to check the nearly normal. Random can be that it's independent, so it's probably random. And then the nearly normal will be checked by looking at a histogram. So the answer is 1.6973. 1.6973. There we go. Now we simply plug in the numbers. The mean is 8155 plus 4 minus 1.6973. Standard deviation is 1664, square root of 30. It's just solve out the problem now. Plug in the numbers, solve out the math. 1664 and times 1.69. There we go. 51. This is the margin of error. That is that quantity. So we're basically adding 51565. So 5. Let me write down right here. 51565. So there it is. And we're just going to add and subtract this to get the lower and the upper. So it's going to be like 760 and 870. 8155 minus 515. 76. Let me copy that in. And then 51565. Round to the nearest whole dollar. And we just added 51565 to the value of this right here. And that'll round up. And we've done it. Wait, what? What? Round to the nearest whole dollar. What error did we make? Let's take a look. Is it not 51565? Okay, let's look. Let's check the margin of error again. If you saw what error I made, please let me know. T times S over square root of n. Okay. Square root of n. There's that. There's that. Times 1 point. Oh, no. That's going to make it a tiny bit. John, I owe you. I used the degrees of freedom. Oh, John, 50,000. Literally, you know what that means? Because we're dividing by a bigger number, so it should be a little smaller. That's why you know your notation, brother.
Notation,
so the interval should be a little bit smaller. So my guess is it does that. It does this. It's close. It's close. Watch it be 1 off on that. It's going to be very close to this, but even smaller than that is interesting. Okay, so there was this error here, as John points out. This is n, and I put in the degrees of freedom because I was still thinking the 30. So there's the problem, which will change the margin of error down here, and 515. So that means 31 square root, and that's not 31 square root. What is wrong with me? And then 1664 divided by this times 1.6973. 515, that's a difference of 8. So that means I have a difference of 6. So it should be this, and it should be this. There we go. And you literally will just take and do this. Does that make sense, John? Literally the answer is this right here. The answer is going to be, you did the, oh no, because I told you. Because I put the degrees of freedom in for the n. If it had just been like a larger sample size, it probably wouldn't have made a big difference. But the answer is 8155 plus 507.26, round to the nearest number. So just know your notation. A lot of this mark comes down to notation. One error on notation, and then you get something wrong. Why? Okay, next one. Yeah. 27, 4 to 3. Problem 4. The housing market has slowly recovered. Let's look at what they got. Suppose the standard deviation of these losses had been this instead of this. What would this do to the confidence interval? So if there's more variation in the losses, the interval will be wider. Don't even read their answers. If there's more variation in the losses, the interval will be wider, which is standard deviation. If there's more variation in the losses, the interval will be wider because y bar plus or minus t bigger. Because it's this. They're saying this gets bigger, so that's going to make the margin of error bigger. So the interval would be bigger. A larger standard deviation would increase the width of the interval. Mathematically speaking, it's going to make that s bigger right there, so that's what it would do. A classmate suggests that the margin of error could be reduced if the confidence interval changed from 90 to 95. Do you agree? Do it with your hands. 90, what do you want to say when you say 95? If you say 90 and then you say 95, what is your hands going to do? They say the margin of error could be reduced if you change to 90. Oh, change to 90 instead of 95. So they're saying you're at 95, they want to change to 90. Yeah, it gets smaller. Because 95, 90. And we can view that visually. Oh, take a nap. 95, 90. Gets smaller. And so yeah, definitely lower confidence, tighter interval. Instead of change the level of constant confidence, would it be more statistically appropriate to draw a bigger sample? I'll just say yes. Yeah, you don't usually just change your confidence. You take a bigger sample, and this would change the n. And by taking a larger n, you divide by a bigger amount, and that makes the margin of error smaller. So the margin of error will decrease, which is the plus or minus when you take a bigger sample size. So a larger sample size would reduce the standard error of the mean. That is true. The way they phrase that, because what they're saying is they're talking just about this component getting smaller, which is true. But if that component gets smaller, the margin of error gets smaller. Because they're saying, because let me just point out, S over square root of n is known as the standard error of the mean. And so they're saying this quantity right here is going to get smaller, which then in turn makes this smaller. So it makes sense. I would just say it makes the margin of error smaller. Easy question. Let's do it in seconds right here. If you take a sample of 15, what's your degrees of freedom? You take a sample of 15, what's your degrees of freedom? You take a sample of 15 for one sample t. Did they explicitly say that? Yeah, confidence interval for the mean, which is a one sample mean. 14. Yep. N minus 1. Done. There's test questions like that. There's a few. Livestock are getting fed. Good old livestock. I think ag is fun. I've been on cow farms. You go in, they just look at you. Cows look at you. Livestock are given a special feed supplement to see if it will promote growth. Researchers report that 77 cows studied gained an average of 56 pounds. That's with a 95% confidence interval with a mean, with a margin of error of 11. So what's the interval? It kind of says it. But how would we, I want someone to write an interpretation of the interval properly in the chat, and then we're going to look for that. What is the proper interpretation of this interval? Don't even look at their answers yet. Think we are talking about cows and weight gained. So like the true weight gain for all cows that would eat this. What is the interpretation of it? I want a proper interpretation. What is the proper interpretation of it? What is the proper interpretation? Give it a shot. Don't even worry about what they write. Because they're going to try to trick you. This one has multiple, like, is this right? Here we go. I am blank percent confident that the true blank is contained in the interval blank to blank. We are 95% confident that the true weight gain of cows, yep, for like all cows that eat this feed, is contained in the interval 45 to 67. Nice job, John, right there. So 95% of the cows studied. No, we're not talking about the cows studied. It's for all the cows. So this interpretation is wrong. The confidence interval is for the population mean, not individual cows. It's about I am 95% confident that cows that take this supplement, not one cow. One is 95% sure that a cow, no, it's not about a cow fed this supplement. It's about the truth for the population. So the confidence interval estimates, nope. One of one. The confidence interval is not for individual cows, yeah. And if this says the confidence interval estimates the population mean, that would be right. The confidence interval estimates the truth for the population, not for individual cows. They're trying to trick me with that one. One is 95% sure that the average weight gained among the cows in the study. What was the average weight gain in the cows in the study? It literally says it right here. It says it was 56 pounds. So you don't make confidence intervals to estimate for the study. You make confidence intervals to estimate for the truth. We know that the cows in the study gained 56 pounds. So we know the average weight gain of the study cows was 56 pounds. We don't make an interval to estimate that. The average weight gain of cows fed this supplement will be between... This is close. I feel like something's a little bit wrong. The average weight gain of cows fed this supplement will be between... Yeah, that's... Okay, they're going for... Okay. Wow. This is very close to true. And I'm a little mad at the way this is phrased. What it is the truth is something that exists. And the truth... Like when someone... A very bad interpretation people hate in statistics is the truth falls in the interval. Like a lot of statisticians, including myself, don't like that idea that the truth falls in the interval. Because if you make an interval, the truth is static. Like this microphone is the truth. The interval might contain the microphone. So we wouldn't say the average weight gain of the cows fed the supplement will be between this. No, it's that the interval might contain the truth this percent of the time. So it's not that the average will be in there. The average weight gain of the cows does not vary. It is a constant value, which the confidence interval tries to estimate and might contain. That's very theoretical. They went really hard theory on that one, or very like minutia. If the supplement is tested on another sample of cows, it's not about samples of cows. It's about estimating the truth. There's a 95% chance that their average weight gain will be between this and this. That doesn't sound correct. So there's a 95% chance that another sample of cows will be within 2 standard deviations of the true mean. Yeah, that's because this is going into the idea of samples from sampling distributions, that if there's a truth out there, which there is, for how much these cows would gain, then the cows would be at least 2 standard deviations away from the truth 95% of the time. But that's not what this interval is trying to do. I hope people get something from that question. I can't decide if I hate or love that question. The answer is, I am 95% confident that the true weight gain of the cows is contained in the interval 45 to 67. That's the answer. Because we're trying to estimate the true weight gain of cows that are in this. Okay, last one right here. I don't know. I kind of like the question, but then I wish they gave you one right one. I wish they gave you a right answer to C. Yeah. A biology class conducts a study on burbs. Because burbs aren't real. I I mean, I think they're real, but some people say they aren't. Using the number of species counted each week, a student finds a 95% confidence roll from 16.34 to 18.69. What? Decimals? For the mean number of species counted, knowing that species have to be whole numbers, like you can't have a 16.34 species amount, the student reports with 95% confidence that they saw 16 or 17 or 18 species. It's not how we do it. So when we say things like the average family has 2.5 kids, we're not saying there's a 0.5 kid, even though I'd probably be that kid. What does that mean? I don't know. So with this, they're saying that on average, there's this many species when they birdwatch, which can have decimals. Someone says to you, how many pizzas do you eat a week? And you go, I don't know, about 1.3. And they go, you order 1.3 pizzas? And you're like, no, like 1.3, because most of the time it's 1, but sometimes it's 2. Maybe about every third week I order a second pizza. What you mad at me for here? What you doing? So you can have decimals when it comes to means. Is it a confidence roll only estimates the sample mean number of species? Well, very close. Is a confidence roll, Rylan? Let's throw you 50,000 points, Rylan. I appreciate you. I want people to answer every question. Does a confidence roll? Yep. Great job, Rylan. We're throwing you 50,000 for being here and answering. It is C. Confidence rolls estimate the truth for a population, and that's kind of the goal. Is that a confidence roll estimates the truth for a population? And the true mean can have decimals. We kind of talk about that a lot here today. I think today's lecture was jam-packed when we talk about intervals where we try to figure out the true mean of a population. So good work, Rylan, right there. Tons of points during office hours. Should we do what should we do? 1 or 2 more? Might head around 210 or so. But who got the full homework done? Full homework done. I don't think it's even due for a while. That is the full homework done. Got it done. W. It's not even due till a week from now. We're a week ahead. Just tell people, be like, hey, like 30, 40 minutes? Yeah. Oh, and you got 13 quiz. Rylan, do you have 13 quiz done with 100? Did I just do a few problems and they figured out the rest from the theory? That makes me, if that's true, that you got 13 quiz. Did you get it all? Rylan, I don't care. I'm doing 50,000 points on my own. Wait, that's my copy paste of. We got to get people's points higher. Tell people come to office hours. He's just gone mad with points. Ryan, that's amazing. I'm really proud of you right there. That's a really productive 30 minutes or so. Allie, good to see you there. Point City here. Got to get people excited. Alexis too. Braden. Oh, wait, how many people we got here just watching? Just got them here, but don't worry, I'm here. Allie, why not? Point City. What should be our last problem? Let's find a really hard chapter 13 problem that people are going to get stuck on. I think I do have one that people are going to be like, how in the heck do you solve this? But it's actually an easy solve if you know the tricks. And I do have a lot of these in videos that can be found elsewhere. All you have to do is search the YouTube channel and you can find pretty much a video on any problem. And we already have the full chapter 13 homework in a video from last week. But please feel free to ask. Let's do it. You are here. You've asked. 2012 Gallup 13 quiz. That is the question we will do, Alexis. Let's do it. I don't think it's this one, is it? If you see it, tell me if you see the number, Alexis. Is question 1? It's not this one, is it? I don't think it's this one, right? Tell me if you see it. Be like, oh, it's question 3. There's all these polls and Gallups. I just We did that one. Here it is. Oh, this is a good one. I like this one. Time for 2 more. Okay. The margin of error is mathematically what or visually what? When you think about the margin of error, it is what the length of the interval. You should memorize this. The margin of error is what the length of an interval. Half the length of the interval. Half the length. So, do they not give us the interval here? So, this one, it's kind of weird. I thought I loved it. It went down to because they're trying to trick us. Let's look at what they give us. I thought they gave us the interval, and I was like, ooh, that'll be easy. So, what I mean by half the length of the interval, if I tell you a steak is going to cost between $30 to $50, what is the margin of error of this interval? From 30 to 50, the margin of error is what? What is the margin of error? What is from 30 to 50? If this is the lower and this is the upper, the margin of error is what? This isn't this problem, but it's the idea. It's 10. Yep. Because you'd say 40, it's 10. It's 40 plus or minus 10. So now, my pen has an eraser. I got to remember that. Let's look at what they gave us for this problem. So this problem says they talked to this many adults. That's sample size. The ones that were baseball fans is this. And in February, only blank of a smaller sample size reported being baseball fans. So this is recent, and this is p hat from February, like an older p hat. Oh, that's all right. That's all right, Alexis. I think this is the right one, right? As long as it's the right one, totally good. This is going to be the z-score, and it's 1.6449. And we can know that by going over to the applet, and we enter in, we got to be on the z-score applet, the normal applet. So we go over to normal applet, and we go between, and we do this right here. And you can go to 4 decimals. You're probably fine if you do 2. But this is the apps page right here, which can get you the z-score. So there it is right there. Which poll are they asking about? For the margin of error of the 2012 poll, if we want 90% confidence in our estimate of the percent of U.S. adults who are baseball fans, find the margin of error. Okay. So for the margin of error right here, we need to get Q hat also. And I think they're talking about the top one. I wish they didn't give... Oh, that's 2008. That's 2008 is the old one. So P hat of this current one is 0.484. And Q hat, who knows Q hat? Find me Q hat right here of this top interval. So remember Q hat is Q hat equals 1 minus P hat. Go ahead and find it real quick. And the margin of error, I'll write it out for you. So I'm writing this as you find it. P hat plus or minus Z P hat Q hat over N. And this is the margin of error. It's everything after the plus or minus. So the margin of error is after the plus or minus. So this is the margin of error. Great job right there, Rylan. Yep, just 1 minus. So, and you can add them up to make sure they add up to 1. And so now we're just going to plug into here 1.6449. Then we square root 0.484 times 0.516 over 1006. And this will solve to the margin of error right there. I will solve to the margin of error. 0.484 times 0.516 square root times 1.6449. And that should be it. I think I've done it. I think I have. There's that to 3 decimals. Good. Explain what the margin of error means. One is 90% confident that this poll's estimate is within this much margin of error of the true for all baseball fans. I think that's right. If you wanted to be 99% confident, the margin of error would be bigger because you're going from 90 to 99. To be more confident, intervals need to contain the truth more often. 90, 99, you spread it out more. We can also see that visually right here. You go to your applet and you go up to 99% confidence, and you see the interval gets bigger, making the z-score bigger. And if you make the z-score bigger, which is this right here, you'd have a bigger margin of error because you're timesing by the z. So to be more confident means a bigger interval. To be more confident, the interval is contains the truth more often, which means a larger margin of error. The second one here is going to be very similar, but it's from a smaller... Oh, wait, it doesn't say the sample size? Oh, why did it give the second one? Why did it give that second thing? It just wants us to go to 99% confident? Okay, we just changed the z-score. The z-score, if you didn't see it, was 2.5758. There's the z-score. I like the 4 decimal places. So literally all we do is we go in here and change the equation and type 2.5758. There it is. That's got it. And so what we could do is we could divide by 1.6449 and then times by 2.5758. Dividing by it undid this right here, and then we multiplied. And if you don't believe me, I'll carry it through. So it's 0.484 times 516 divided by 0.16, and then square root times 2.5758. There it is right there. And 3 decimals. In general, if all other aspects of the situation remain the same, will smaller margins of error produce greater or less confidence intervals? What's saying, if all aspects of the situations remain the same. This is such a weirdly worded question. If all other aspects of the situation remain the same. It's... Oh, I see what it's saying. This is such a weird way of wording it. It's such a ridiculous thing. Okay, let me explain. Because it's going to be counterintuitive, I think. If all other aspects remain the same. In general, if all other aspects of the situation remain the same, will smaller margins of error produce greater or less? I can't believe I'm like, if all other aspects, because I think they're talking about like sample size and stuff. I really don't like the way they phrase this because it doesn't, I think what they're saying is you have a smaller margin of error. And Z, everything stays the same. It can't stay the same. Oh, it's saying, maybe it is saying everything stays the same. I think, so it's saying if all other things like the sample size remain the same, will smaller margin of error, it'd be less confident. Okay. Just the way they said that. It should just say, I think because they're like, well, if someone overthinks this, it's saying if Z decreases, margin of error decreases. That's all it's saying. It's saying if you decrease the confidence, you make the interval smaller. Does that make sense? Do you follow me on that, Riley and Reptar? If you decrease the confidence, like if Z goes down, if Z gets smaller, which is related to the confidence level, then the margin of error gets smaller also. So if Z decreases, yeah. And it's saying like, you can't change these other things because someone will be like, well, what if N gets bigger and Z gets bigger? It's like, no. It's like, don't even worry about this stuff. It's like, what does Z do to an interval? Just, I thought they were going for like some really crazy, like if the I thought they were like way overdoing it and I was going to overthink it. But they're saying, what does confidence level do to an interval? Yeah, I know, right? I literally was like, I don't remember it being this crazy. DeMarcus, good to see you there. Well, stats try to trick you. We've got the full, if you weren't here for the full thing, we've got the full chapter 14 homework here. We also have who's working on chapter 13 homework because we have that in the video too, and I can drop that here for you. Really appreciate everyone being here, but we have chapter 13 homework if you haven't done it all. Mubot trying to advertise for us. Thank you, Mubot. But we have chapter 13 homework from a previous office hours, and so check out these office hours and do the homework and do the quizzes. Here is the chapter 13 homework. Maybe I'll put it in this video too. Like, wonder if it'll work. Chapter 13 homework. There we go. There we go. With that, bye for now, everyone. Good seeing DeMarcus. Bye, everybody.